Wow, most awkward transition ever. Sorry guys, I don't have time to re-record this, so we're just going to go with it. So we were talking about the fact that we know the mass of the compound, which is 13.6 grams. We know the mass of the element oxygen, 5.40 grams, and we were able to calculate the mass of the magnesium, 13.6 grams, and minus 5.4 grams, and it gives us 8.2 grams of magnesium. So now to calculate the mass percent, let's actually go back and let's calculate specifically the mass percent of oxygen first. And so if we want the percentage of oxygen, we're going to do the mass of oxygen that they provide for us, which is 5.4 grams of oxygen, divided by the 13, oh, that was nice, 13.6 grams of compound. And then we can multiply that by 100, which gives us a percentage of 39.7% oxygen. We can do the same thing for magnesium by taking the 8.2 grams of magnesium that we know is in the compound and dividing it by the mass of the compound, and then multiplying by 100. And when we do that, that is going to give us 60.30% as the percent mass of magnesium. And again, we can check our answer by adding these two, and they actually do add to 100%. Yay, math. So we were able to find the percent composition even though we didn't know the ratio of oxygen to magnesium. But wouldn't it be nifty if we could take data like this and actually figure out what the formula for the compound was? And lucky for us, we can actually do that. When we consider determining the formula of a compound, there's a couple things we have to think about. The formula of a compound represents the ratio of elements in the compound, and in the past we've referred to that as the mole-to-mole ratio. So if we look at an example, we can talk about styrene, which is C8H8, and the molecular formula for styrene is C8H8. This molecular formula is the exact formula of the compound. It tells you exactly how many carbons and exactly how many hydrogens are in the compound. The empirical formula, on the other hand, is the lowest whole number ratio of the elements in the compound. So the empirical formula for styrene would be CH, because it's a 1-to-1 ratio. But that doesn't tell us specific information about how many carbons and how many hydrogens we could expect to see in styrene. It just tells us that we should expect to see the same number of carbons as we see hydrogens. And so we could write that as a 1-to-1 ratio. When we say that we want to determine the formula of a compound, it's important that we indicate whether we want the empirical formula or the molecular formula, or sometimes we want both. And so let's go ahead and do an example, and I will show you how to find an empirical formula and actually use that formula to find the molecular formula. If we have a white powder and we analyze it and it contains 43.64% phosphorus and 56.36% oxygen by mass, we know some information about this compound. Additionally, we also know that the compound has a molar mass of 283.88 grams per mole. ultimately, we would like to figure out the empirical and the molecular formula of this compound. So to do this, we're going to take it in two steps. We're going to start by establishing a mole-to-mole ratio of phosphorus to oxygen, and then we're going to use the molar mass to determine the molecular formula. So let's start with the empirical formula. The first thing that we have to do is decide what kind of sample we're dealing with. So I like to assume that we have 100 grams of the compound. So 100 grams of sample. This makes our math very simple. Let me show you why. If we have 100 grams of sample and I want to know how many grams of that 100 grams are phosphorus, I can use my percent by mass for phosphorus to figure that out. So phosphorus was 43.64%. I changed this into decimal form in order to use it for calculations. And the whole compound is 100 grams, then that actually means that the mass of phosphorus in the compound is just 43.64 grams. So we can use the percentage for phosphorus and also for oxygen like grams because we chose a 100 gram sample. This just makes our math really easy. So we want to figure out how many moles of phosphorus we have. So what we're going to do is we're going to use how many grams we have, and we're going to go to moles. If you think about your mole roadmap, we're starting with grams. So we're starting at the purple stop sign, and we're moving through to the red stop sign of moles. So we're going to use the molar mass from the periodic table, and we're going to divide by that molar mass. So for phosphorus, we have 43.64 grams, and we want to take that into moles. So we're going to use the molar mass, which is 30.974 grams in 1 mole of phosphorus. So we wind up with 1.41 moles of phosphorus. We can do the same thing for oxygen. We have 56.36 grams of oxygen. I got that from the percentage of oxygen right here. I'm going to use the molar mass of oxygen, which is 16 grams, to calculate the moles of oxygen involved, and that is 3.52 moles of oxygen. So now I know that for every 1.41 moles of phosphorus, I have 3.52 moles of oxygen. But we never write decimals in molecular or empirical formulas. So we need to transform these decimals into whole number ratios. The first step to doing that is to pick the smallest molar amount. So in this case, that's phosphorus. Now I'm going to make whole number ratios by saying that for phosphorus, there's 1.41 moles of phosphorus divided by 1.41 moles, and so my ratio is 1. For oxygen, I'm going to do the same thing. We have 3.52 moles of oxygen divided by 1.41 moles, which gives me 2.5. So now I still don't have a perfect whole number ratio, but I can see that I have 1 to 2.5, which, if I multiply both sides by 2, becomes 2 to 5. So that means for every 2 phosphorus, I'm going to have 5 oxygens. So this is the empirical formula. So when we're solving these types of problems, it is all about the ratio. Okay, so now we have our empirical formula. This is really important. We're going to need it. So I'm going to write it up here at the top before I erase everything to make room to calculate the molecular formula. Now that we have some space to work with, let's go ahead and calculate our molecular formula. So to do this, we know that the molecular formula is just a ratio of the empirical formula. So we can use a ratio between the molar mass, which we're given, and the mass of the empirical formula. So that looks like this. We would take the molar mass divided by the empirical mass. And we calculate the empirical mass in the same way we would calculate the mass for any compound. So I'll take the number of times phosphorus is in the compound multiplied by the molar mass of phosphorus, and then I will add the number of times oxygen is in the compound times the molar mass of oxygen. And when I add those two together, I get 141.948 grams per mole. All right, so we have our empirical mass and we have the molar mass that they gave us, so we're ready to set up our ratio. So we've got 283.88 grams per mole divided by 141.948 grams per mole. And if we work that out, it comes out to be right around 2. So this means that there are 2 empirical formulas in one molecular formula. And so to calculate my molecular formula, then I would take my empirical formula and I would double it. I would multiply by 2, which would give me P4O5. And then if we added up the molar masses on the periodic table of phosphorus and oxygen in 4 and 5 respectively, we would find that it is equal to the molar mass that we were given. So this is kind of a multi-step problem. You have to first assume a 100-gram sample, and then you use the grams of each element in the sample divided by their molar mass to find the moles of that element. You use the moles of each element to set up some mole ratios, and that allows you to find the empirical formula. And once you've done that, you can use a ratio between molar mass and empirical mass to find the molecular formula. We will practice this for the rest of this week. We will also do one example together as a class at the end of class today.